Welcome, everybody. Our first speaker for this afternoon session is Claudio Freire. He is coming to us from Argentina. He's a frequent speaker at PyCon Argentina, and this is his first time at PyCon US, so please give him a warm welcome.
Hey there. Well, thanks for the introduction. Maybe the slides. Great. Okay, so this is kind of redundant. First, how are you? Good afternoon. Hey, great. So we're here to talk about Python, of course. It's a PyCon. And I would like to talk about sharing stuff, mostly memory. So if you've ever tried sharing stuff, like CPU or whatever, with Python, you might feel like that, right? I mean, Python doesn't make it easy. Like the GIL, basically the way threading doesn't let us really use multiple CPUs, makes us need multiprocessing, and we cannot share objects if we do multiprocessing. So I'm going to talk why I wanted to share memory, because there are many reasons. Some people ask, why do I need to share memory? I mean, I know you don't, because you're here, but some people do wonder, why would I need to do that? So for me, it was because, well, I had lots of caches, dictionaries with cache stuff, and I couldn't fit them several times once per processor. So, I mean, they could fit all in memory once, but not 30 times. So, for me, that was the motivation. Also, another motivation that appeared later when I had the means to share memory was like, okay, now that I have this huge data set. It doesn't fit in memory, but I know I won't be accessing all of it. So maybe the operating system can do the swapping magic and do I/O for me, and I don't need to do I/O. So that's one. It also happens sometimes that, yeah, you can talk to a database, you can talk to memcache, you can do other stuff, and it's OK. You can work like that, but serialization is a bitch, right? I mean, it consumes CPU. It's really tricky to make everything peak level. So that's another motivation. So how do we make this transition to shared memory, which I call shared buffers, because I know why not. I do a lot of Postgres, and Postgres calls it shared buffers, so maybe that's why I called it like that. Well, for the caching architecture, which is what I'm familiar with, the trick was to have all the information divided in two. You have the part of the data that doesn't change much, because if you have like 50 gigabytes of data, it's possible that it doesn't change all the time. It's hard to make 50 gigabytes of information change all the time. So you will have a read-only layer for the stuff that doesn't change, and then something else for the stuff that does change often. So I call that a read-write, read-only layer. The read-only layer is going to be the stuff that we can easily share in memory. The trick is that the read-only layer should be rather big compared to the read-write layer. So somebody asked, why not use multiprocessing stuff? Multiprocessing gives us shared C types, it gives us shared arrays, stuff like that. Well, in my opinion, first, in my experience, using that for writable stuff creates lots of log contention. I mean, it becomes slow. But also, it's really difficult to use those primitives to put objects in shared memory. I mean, if you've ever tried, who has ever tried that? Nice. Not many people, I see. But it's tough. And there's this little quote that I really love from the documentation. Even though you can put pointers, I mean, pointers are the basis of all complex data structures, right? So if you can put pointers in shared memory, but then your application will crash. So yeah, great. So I want the best of both worlds. I want to do multiprocessing. I want to have cache. I don't want to waste memory copying stuff n times. So I divide, like I said, I divide everything in two. First, a buffer that will be encoded as all the whole talk was going to be about that, so we'll see. And then the read-write layer, for me, was the process's memory or a memcache server somewhere. Yeah, it's going to be a little slower, but it works. The shared part is quite simple, in fact, because there's a very easy way to share stuff through memory mapped files. I mean, who gets what that is in here? Not many. Okay, for those who didn't raise their hands, maybe you're asleep and that's why. But you can have a file that has lots of data in it. You can call a library that's called memmap, mmap. Well, it's hard to read, but it's memmap. And tell it, OK, put this file in memory and give me all those bytes. And the nice thing about this is that the kernel, the operating system, knows that if you have several processes doing this on the same file, it won't have n copies of the memory. It will just use the same memory for those contents, especially if all you do is read. If you write, it will have to copy because otherwise you'd be changing someone else's memory, but you can tell it not to copy, so then you can share stuff and write. But how do you put objects in there, right? That's what we want. And memmap gives us bytes, which is something, but we want to put objects there. So the trick is, of course, defining a schema, like a shape the data will have. The schema has to be easily manipulatable, if that's a word. It has to be easy to read, to write, and it has to be efficient. I don't want it to be huge, right? I want an integer to be like 4 bytes, pretty much, ideally. And I need the machinery to do all that in a Pythonic way. I don't want to work with protobuf, sorry. So basically, the trick I found, the trick everybody will think about is like, OK, to manipulate bytes into structured data, we have struct. And Proxies lets us shape other stuff and make it look Pythonic. So we'll do that. No biggie, if my remote works. OK. So with struct, it's rather simple. Import struct, pack, unpack, all the stuff you probably already know. But that's kind of inconvenient. In C, I know this is PyCon. You don't want to hear about C. But in C, I just can define the struct and do point A, dot B, dot C, and just use it. I don't have to go around packing and unpacking. So that's what I want to do. But I don't have C, right? So why do we get C into this? Well, there are many reasons why we want to think in C terms. First, C structs are very, very portable. Like lots of languages, most of them really, need to work with C structs, so they support some way of parsing them, reading them. Also, if I can get C code in there somehow, because CPython is written in C, why not? I will be able to access that data natively. I don't need to serialize or deserialize anything. I can just work with that information. And because we can write Python, we can write C as if it were Python with Python. So that's what I do. It's not trivial. The Python you write reads more like C than Python, but OK, it's what we got. But we end up with something really Pythonic from the outside. Don't look inside. That looks like this, right? It's really nice if you can do this. Basically, the proxies let us look at the shared buffer as if it contained objects. You have to tell it where the object is. And you do .a to get the A, .b to get the B. And in no at no place you're like really serializing stuff. You're not just reading the whole buffer and loading it into memory because that's pointless. So this is the thing, but how do we do this, right? Well, the benefit of doing this is, like I said, it doesn't require serialization because you go where you need to when you access that information. Also, if you go back, we can change the offset really simply. Right? That proxy has an offset inside. If I want to point to another object, I just change the offset, and that's it. And so I don't have to create Python objects to work with the shared memory, which would defeat the purpose of sharing the memory, because Python objects are not shareable. And thanks to duck typing, proxies actually quack like whatever they're proxying, so they look like whatever they're proxying for the other code. So I can use them in place of the original object usually, and it just works. Now, how do we do this? Well, in C, I would like a proxy to have the object in the buffer to have a shape like this if I want to put an object. Imagine a node, a tree node, that has a value left and right, right? The left is a pointer, actually, a reference to another node. Right is another reference to another node. We know how to encode in the buffer the 3. With struct, we encode it as an integer. 3, that's easy. But how do we encode the reference to other objects? Well, there are many ways of doing this. I found the most convenient way was to use another integer to hold a relative pointer. Basically, I hold the offset where that other object will be relative to the offset that's containing the reference. Making it relative makes it able to move around easily without having to rewrite all pointers. So we can easily write code that interprets all this and makes it nice for the outside world. If you work with properties, you will get that code, maybe. It's a little bit ugly, but it had to fit on the slides. But if you don't, basically a property is an object that when you assign it to a field on a class, it tells Python to actually invoke code when you access that property, that attribute, instead of reading an attribute. So basically, when I do, with that proxy, when I have an instance of complex proxy, if I do instance.a, it will invoke the get method in any property, and that method will go and reach into the object and unpack the integer there. This doesn't look very efficient, but it can be made efficient with Cython. With the object references, it's a little bit more involved, but not that much. Basically, I just unpack the relative pointer. I compute where the real object is by adding offsets. And I build another proxy to that other object. I just build a proxy. I don't do anything else. So it's efficient. I mean, the other object could be huge, but I don't care because I'm just building a proxy. So this looks very nice, like a few lines of code, and you have everything. It's like magic. But when you get to it, when you start working on it, you realize there are some caveats. Like, for instance, when you have complex data structures, you end up with cyclic references, and they are tough because then you never stop building your buffer. You try to build your buffer, your file. You start writing, okay, this object, this object, this object. Oh, this object contains another object, so you write it. Okay, this one contains another object, so you write it, but that other object was the first object, but you don't realize. So you start on a loop, infinite loop, never finish. Then your computer runs out of disk, and everything goes to hell. So you have to be careful with that. There's tricks to do that, or you can just say, fuck it. I don't want cyclic references. If you do cyclic references, my library doesn't support it. That's an option. If you're not using data structures with cyclic references, good for you, but I am. So I solve it. So a way to solve it, that's very nice. I'm sure there are other ways, but is to have an ID map. An ID map basically maps the address of the object, an identifier of the object that I'm trying to serialize to the offset. So when I'm writing objects, like I said, if I find an object I already wrote, I just put the offset and don't write the contents. So that breaks the cycle, and it even makes the file smaller. So there are tricky points. I'm not going to go into much detail because I'm running short on time, but pretty much the identity map has an issue that if you destroy objects in memory, you have to make sure to also destroy them remove them from the identity map, or you get trouble. And also it can get rather big. At this point, you're thinking, okay, this guy was talking about no serialization. Why is he talking about basically what amounts to serializing here? Because what I want to do is be able to read the file without serializing stuff. I'm OK with making it an effort to write the file. If you are not OK with that, we can fix that too. But I'm not going to talk about that because there's no time. But it's possible. So let's look at what objects look like inside. First, we have an attribute map. Basically, not all attributes in all objects. I mean, if I have a schema, it's not going to be perfect. So some attributes won't be there. Some attributes will be none instead of an integer. So that's why it's there. Then I'm going to have the attributes that I defined in my schema. The schema basically is the properties. When I define the property, okay, the integer is on offset 0, the left reference is on offset 4, and all that. That's the schema pretty much. So that's what I have here, an integer of offset 0 on the object, then a float in this case, it's another example, and then a reference to another object. The reference is going to be 8 bytes because, I don't know, 64 bits. Why not? So it points somewhere. It points to another offset that has a string. A string is variable length. So there it is, a variable length string. Of course, I'm going to need not only the contents of the string, I'm going to need also the length of the string to be able to interpret that, but it's going to be a string there. Or I could have an object there, right? Another object. So basically the same structure that I had before, I just repeat it there, and it's the same thing. I have a pointer to another object. I mean, a string is an object, so it's the same thing. So I'm going to have another attribute, bitmap, an A, B, so I can have my tree like this. But I don't know if it's a string or an object, so I'm going to want to add a type code, something that tells me what I have there, right? What do I have there? So the type code is a little byte that tells me, okay, you have a string here, you have an integer here, you have blah, whatever here. Nothing, it's not rocket science, right? I mean, who's lost at this point? Nobody. Or, okay, I'm impressed. So what about lists? No, I didn't talk about like complex stuff. I mean, objects are like, they're baby stuff. So lists are very simple. You can imagine lists as just objects with lots and lots of attributes that instead of attribute names, they have indexes. So a list is just a lot of pointers. I'm going to need to write the size of the list somewhere and then just index. So the list of pointers, I call it index. Why not? I mean, it makes sense. And each item points to another object that could be an integer, could be a string like we talked about, or an object. And I can write here, right? Because I can reach into the buffer and change the integer here. It's rather simple. Or I could reach into the index and change the pointer to point to another object. Like in this graph, the object already existed in the buffer, but if it didn't, I can just put it somewhere and point to it. So it's a dynamic structure. I may not be able to add items easily to the list because otherwise I would have to move everything, and it's quite a chore. But I have a limited ability to modify the buffer. What about maps, dictionaries, right? We need to be able to have a dict if I want, like, I don't know, an index of phone numbers for someone. So I like to use a term compact hash table, but then there's a compact hash table in Python 3, and it's confusing. So, sorry. But my compact hash tables are basically sorted arrays of triplets with the hash, key, and the value. So since they're sorted by hash, and the hashes are meant to be uniform, I have a known distribution. I know the keys are uniformly distributed, so I can predict where an item will be just by computing the hash. And then I can look at that place, and maybe I will find the item, or it's going to be nearby, so I'm going to do an exponential search and find the actual position. So it's much more efficient than simply binary search. I will show that a little bit later. Or I can even go even further. I found it useful sometimes to just drop all the keys, because the keys were redundant. At least in my case, I found lots of cases where the keys are redundant. I don't really need them. I'm OK with hash collisions. It's kind of like a Bloom filter. Anybody heard of Bloom filters before? A few. Basically, they're imperfect data structures that have some error. So in my case, I had a lot of use for this. So you can make them smaller and more efficient because you don't have keys to worry about. Let's say a compact hash table, a perfect one, without the approximation, will look like this. Just an index like before, lots of hashes, keys, and values. Keys and values would be pointers to an object that's a key and an object that's a value. But the hashes are integers, so I do a binary search there. Like in a concrete example, if I'm looking for Bob, Bob has hash 7. And whoops, OK, Chloe also has hash 7. It's OK, I have the keys, so I go reach on the keys and verify when they ask for Bob. And I find that v2, the second value, is is the value assigned to Bob, and the same for Chloe. It works. It's some effort, but it works. With an approximate hash table, I cannot know really which of the two values are meant for Bob and which are meant for Chloe, so I just mash them together, and I just return both of them. Maybe useful for you. It was useful for me. I don't know. It's an idea. I want to go a little bit into the details of this optimized binary search because it's cool. I mean, we're all here to hear cool stuff, so yeah. I haven't found in the internet much reference to these kinds of algorithms, although there are papers. But imagine we have an array, a sorted array. Like usual, you would use binary search, but you know the distribution of values in here. You know they're uniform. So if I'm looking for 56, I know, and it goes from 0 to 100, I know it's going to be somewhere in the middle, right? So I predict it's going to be here. But the distribution was, in fact, I mean, I theorized it was uniform, but it was not perfectly uniform. So when I go look, it's a 27. Oh, well, sucks to be me. But since it's 27 is less than 56, I know the actual value is on the right side. So I move a little bit, and I check on the right side. I get 29. I'm still way left, so I move 2 spaces this time. Right? That's an exponential search. I move faster each step. So now I have 45. I have to keep moving, and when I move 4 times, I get 87. OK, I have to stop. It's like I moved too far. Now I know the actual value, if it's there, it's between 45 and 87. So I just do a binary search, find the actual value. This is my upper bound, and I find it. So what's cool about this is that first, you read the values around the actual position where your value is. So it's actually very benign on the cache and on the processor memory cache and all the disk cache if you have to do I/O for this. Remember, I said this data set could be bigger than my memory, so the operating system will be swapping. So that's I/O. So also, if I have good predictions, it's going to be much faster than binary search because the actual cost of this, you can prove it, is to log the error. So if the error is small, and it's going to be smaller than the size of the array at least, it's going to be faster. And the approximate hash table is even better because it's constant size. I mean, there's no variable size thing. I mean, the keys are variable size. I don't know how big they're going to be. But the approximate hash table has only integers. So it's really a nice data structure to work with. Like I said, this has the good thing that even if it doesn't fit in memory, not even the active part, I actually put this to the test, and it's really efficient going to disk and even to rotational disks. I mean, rotating Rust. And since the index is small, I can even preload it to memory. It's more likely that the index will fit than the entire thing. So I don't have to do the random I/O for the index search, only for the value search. So it's fun. It's kind of like a database. I mean, who would have thought? And another thing I've been mentioning, but let me mention it again. If you want this to be really fast, if you want attribute access to the proxies to be like attribute access to a real object, you need to cytonize the properties, because otherwise, messing with struct every time is going to be slow. Not terribly slow, but slow. Even if you don't cytonize, you're not serializing the whole thing, so it's not that bad. And a trick I really like using is, like, I have a proxy. Sometimes I have to change the schema, because I go from one object shape to another object shape. Like a node references, I don't know, user. So I need the schema for the user now. I don't need to create another proxy. I can grab the proxy I have and change the type, because Python's really amazing. Lets me do this. And this operation is fast in Python. I was really surprised. So basically, that's it. This link has nothing to do with what I was talking recently. But it's really fascinating read if you like about sharing memory, because it implements memory sharing between Python processes in a completely different way that will blow your mind. So do go around and read it if you're interested. And that's it. Do you have? Of course. Oh, okay. Okay. Questions? No questions? Otherwise, if you want to ask questions, but that you think about later, I'm going to be outside, of course, so you're welcome to ask. Thank you.